Hello, everyone. My name is Istameli, and I work at NCSR Demokritos. So I will present the notebook that Federica shared a while ago, and we will go in more technical details. So first of all, the first step that Federica executed was to download the helper functions that we provide so as to interact with their platform, and also a second script for SpecFem, which downloads the necessary files that need to be registered in the DARE platform. So this is the base URL of the platform, and all the their services use this domain. So let me execute these steps. Okay. So we also provide a credentials YAML file, which you download from this URL, and you need to provide the credentials in the platform and your B2Drop credentials if you wish to use the B2Drop API call, which is in the following steps. So the DARE manager uses some environmental variables to authenticate you in the DARE platform, and only if this fails, it uses your configuration file with the credentials, and you can in this way acquire a token so as to use the following API calls. So in the DARE platform, we provide a share file system to the users, and this is the base path, home MPI user SFS. And inside this folder, each user has its own directory, and it's named after his or her username. Inside your directory, you have three subfolders for your runs, for your uploads, and for your debugging runs if you use our Playground module. So in the helper functions, we provide multiple functions to list all your directories, to find a specific folder or a specific file, to download it, and so on. So as a first step in this use case, as Federica said, you need to upload some input files in the platform. We provide a specific API call for uploading. This function will store your files inside your uploads folder. For example, this is the remote path. For example, if you have a username user1, you will have a path home MPI user SFS user1 uploads. So inside your uploads folder, you can create subdirectories like data, and you specify it with the remote path variable. And inside your subfolder, the input file will be stored. If you do not specify any subdirectory, all your uploads will be stored under the uploads folder. Okay, so this is the same function. Okay, so I will skip the dispel4py code. Okay, so the first step to execute a dispel4py workflow is to register it in the platform. The code is available in the GitLab repository of WP6 EPOS, and by calling this register D4P workflow function, you can register it in the platform. In order to register the workflow, you need to provide a name and the code. The function returns the workspace ID and the ID of the workflow in the registry. So these IDs are stored by the helper functions in this session of Jupyter. But if you want to execute this workflow in other sessions, for example, tomorrow, you need to save these IDs and use them in the execution step. So here is the execution function of the Dispel4Pi workflow, the exec D4P. You need to provide the number of nodes, the containers that need to be deployed for this job, how many iterations. The target can be simple or MPI. You need also to provide the requirements file from a URL, which will be downloaded inside the execution environment. The Dispel4Pi execution environment creates a virtual environment and stores all the additional libraries that your application requires. And you can also provide the input data of your workflow in a dictionary. So here, you do not need to provide any other information if you execute this function in the same session as the registration, because as I said, the helper, the DAR manager stores the workflow information in the session. However, if since you do not need to register each time the workflow, if you want to execute this function outside of this session, you need also to provide the workflow name and the IDs that you saved from the previous step. This function lists all the running jobs of the user. So if you run a Dispel4Pi and a CWL job, you can see all of them if they are still running, their status, and so on. Okay, I will skip also provenance, which Federica showed previously. So with this function, you can list all your directories. So they are separated in three different blocks. First, you can see your uploaded files, then your runs, and the runs from the playground. And you can select a specific directory to list your files. So when you execute a workflow in this Jupyter notebook, the DAR manager stores the latest run. So it stores the latest run directory, which is under the runs folder. So if you want to see the output files, for example, the logs or any images produced by the workflow or something like that, you can execute this function, the list exec folder, without providing any any parameters. But if you want to list a previous, an older run, or you just started the notebook and you do not have anything stored in the session, then you need to provide the name of the run directory. This information, the run directory, the job name, and so on, is provided when you execute the the execution step, the exec D4P or the exec CWL in the CWL use case. Okay, and when you list your folder, you can select download a specific file, for example, the logs, or a specific output file. Again, if you are in the same session, all you need to provide in the download function is the file name. Otherwise, you need to provide also the directory, the run directory, with where the file is stored. In a similar way, you can list a subfolder in your uploads directory and download a file from the uploads like this. You provide the name of the file that you need to download. Here, the kind is upload or runs. So the API searches under your uploads or run directories, and the name of the subdirectory where the file is stored. Also, here, Federica has different workflows in each step. So for provenance, she needs to keep track of the previous run ID. So the DARE manager stores the run ID of each step, and you can provide this information in the execution in the next execution environment. Okay, so regarding CWL, as we said, CWL needs to be associated with a specific Docker image. The Docker image needs to have all the necessary libraries, tools, whatever is needed by the application. So a user should create the Docker file and all the necessary scripts and register them in the platform using the CWL workflow registry. Their API provides an API call to download these files. So the local admin can download and check these files and then build a Docker image. This image should be stored in a public Docker repository like Docker Hub or GitLab registry. And the admin needs to update this registered Docker with the URL of the image. Finally, when the image is available in the registry, the user can also register the workflow, the CWL workflow, and associate it with Docker. So how can you do that? You need, first of all, you need to register the Docker. So you need to provide some parameters, the Docker name, the Docker tag, the script names, and the path where you have your scripts. Using the SpecFem helper, you can download the Docker file and the scripts from the GitLab repository of the DARE platform. So with this function, DARE manager loads all the scripts and sends them to the DARE API to be stored in the registry. So after the registration, the admin checks the files and uses this function, provide Docker image URL, to update the entry with a URL. Okay, so you can see the code here. Okay, so now that the Docker is available in the platform, you can also register the CWL. You need to provide the workflow name and version. Its CWL is associated, can be associated with a YAML file, which contains information about the script, for example, that needs to run and so on. And you need also to provide the path where you have the workflow locally in your machine. So you need to use the register CWL function, providing the information about the CWL and the Docker, and specify that you do not need to register the Docker because this was done in a previous step. This function can execute all the steps, the registration of the Docker, the URL update, and so on. But normally this should be done separately. So that the local admin can check the files and update the Docker entry. Okay, so now that we have the CWL in the platform, we can execute a CWL workflow using the exec CWL function. What you need to provide is optionally some input parameters that your workflow requires using the input data parameter, and the nodes. If you do not provide any nodes, the workflow is executed in a single container. Again, here, if you want to execute the exec-cwl function without running the registration step, because, for example, you have already registered your workflow, you need also to provide the workflow name and version to the function. Here, the monitoring function is the same. You can monitor your job until it finishes. You can also, again, assign into the provenance viewer to see your workflow and see any errors, perhaps, that happened during the execution, or what happened to the data. You can again list your workspace to find your specific execution directory, and you can list the output files of this directory to check the logs, or if all the output files are created. And of course, you can download them locally if you want to check them. Okay, so the next steps are more or less the same. There are other Dispel for Pi workflows, the next steps of the MT3D use case. I think only there is only one. Okay, here. You can also share the output files or any other file, for example, in your upload folder in B2Drop. So in order to use this function, you can share a single file or an entire directory. You need to specify it in the kind parameter. You need to specify the file name that you want to upload. And also you need to specify if you want to upload something from the output files or from your uploads. And optionally, you can provide a specific path in your B2Drop account that the file should be uploaded. And finally, you can use this function, the cleanup workspace, to delete your run folders or your uploads, and use the list workspace to check that your workspace is cleaned. Okay, so these are the functions of the DARE manager. And I will also show you quickly some the instructions on how to install DARE. The instructions are available in our microsite in the DARE platform repository. So DARE platform is based on Kubernetes. So first of all, you need to set up Docker and Kubernetes in your machine. And you need to install some Kubernetes components like the MPI operator, which is used in order to spawn multiple containers for the executions. You need also to download the Rook shared file system from Git and install it. This is used by their shared file system. One other Kubernetes component that you need is Ingress, so that you have a single domain for all their services. And some other tools to easily install Cert Manager and Keycloak. So we use Helm to install Keycloak. Once Keycloak is installed, you need to register the their login component as client and copy their login secret key in the respective YAML for the deployment. And after having configured all the Kubernetes component, you need to download their platform from our GitLab repository. And we provide a script for the deployment to automatically deploy all the components of their platform. And also we provide a redeploy script, which redeploys only the services and doesn't delete the volumes and so on. And you can expose this services like this if you want to deploy a Jupyter Lab like the one we used previously.
Thank you very much, Ceci.
Thank you. Thank you.
Thank you.
Yeah, I just want to show some more details. Okay, for those who want to play with the platform and the MT3D test case. So for example, okay, regarding the input files that you need to run the MT3D test case, as I said, you need some input files. And these files are, first of all, the specific files required by SpecFM. So a parameter file, a file with the list of the stations, and the files that describe the velocity model and the mesh. So these files could be quite complicated to be created. So just for you to test in the next days, we will provide you some template files that you can use in order to test the MT3D test case. And you also need two JSON files as input.json and processing.json that contain all the parameters required to execute the test case. So in particular, in input.json, okay, you set up the test case you are considering, now MT3D, but for example, we developed another one to calculate ground motion parameters. Or you can develop your own workflow, for example, your own test case, I would say. And then under the label of this specific test case, you are going to set up all the needed parameters. You can find some information in the comment of this JSON file for every section. For example, an important part that you have to set up is the files that should be created to describe the initial seismic source or perturbed ones, depending on the source parameters you want to invert for. So here there is all. It means that it creates a file for the initial source solution and also for all the perturbed source parameters. And so for each of the moment tensor components, and then depth, latitude, and longitude. So the first step of MT3D, the first workflow, will create all these files that are required for the simulations and the source inversion. And you have to set up as well this parameter run simulation. That means which simulation should be performed in order to get the corresponding synthetics that are then needed for the source inversion. So if you just say initial, you will simulate the synthetics just for the initial source parameter. But if you want to do the source inversion, you have to simulate all the perturbed synthetics. So it's better to use here all, and this will perform 10 simulations when you execute SpecFM, each one with the appropriate input files, and you will find the results as I will show you. And then you can also set up the parameters of the used codes like PyFlex and PyCMT3D, where PyCMT3D is the one that does the source inversion. Of course, in the template that we provide you, we set up an example of parameters, so you can just test these and then try to modify and see what happens. And another input file needed is processing.json, where you set up the parameters of each of the pre-processing steps that you apply to the observed and synthetic waveforms. So, for example, the frequencies of the filters that you are going to apply to the data or the synthetics or the type of the trend. And you can also modify this file in order to do only some steps, because you just want to process your data or synthetics in a different way from the one we are using in this template. Organize the steps or do some steps and not doing some other steps. So all these input files should be firstly uploaded into this local data folder in the Jupyter Lab, browsing the files in your computer. And then, as I showed and also CC did, using the upload file function, you just upload those files from this local repository to the remote path of the shared file system. That is the subfolder data. And as soon as you have uploaded those files, you can also check, as CC showed, that all the files are there and are uploaded in the directory. Okay, since in the first part of the webinar, we executed the Display4Py workflow to create the initial input files, we can now see the output just for you to have an idea of how the workflow works. So after the execution of this first step, you can check using the list upload folder function under this subfolder called data of the uploads folder. You can check that all these CMT solution files are available. If in the JSON file you set all, this means that you have to have one CMT solution file for each of the parameter of the source, like the 6 components of the moment tensor and the latitude, longitude, and the depth. So this is the output of the first step. Then the output of SpecFM. So SpecFM produces synthetic seismograms in ASCII format. And so you can find these files under this subfolder, workflow data synth. They look like this. So they are .smv, one for each component of each station. This is for the synthetics for the initial source solution. If you are simulating the files for the perturbed source parameters, so the derivative synthetics needed for the inversion, you just look under the folder deriv. So all the output folders are, okay, now we don't have the SMV files because, of course, in the simulation that I did for test in the first part, I just put initial in the JSON. But of course, okay, you see all the synthetics. Then there is the step to download the observed data, in this case from Ada. So the output are observed seismograms in mini-seed format under this workflow data/data folder. So you see again, you have one seismogram for each component of each station. And then you will also have some XML files describing the parameters of the stations under this folder, stations XML. So these are all the inputs required to the next step, that is the pre-processing of data and synthetics before doing the source inversion. And the output of preprocessing is under workflow data output PR. So this means that when you run this step, you have to check that under workflow data, there is this output folder. Otherwise, something went wrong in the execution. And so under output PR, there are two folders with the preprocessed synthetics and data. And finally, the output of the last step is the output of PyFlex, that is a text file with the windows. For example, you can download this file and look at it. I previously produced it. So this file contains the list, couples of data and synthetics and the selected windows useful for the source inversion for each couple of data and synthetics. And all the output of PyFlex are under this directory, workflow data results measure. And there are also some figures containing the comparison of data and synthetics and the selected windows. And final output of PyCMT3D are here under workflow data results inversion. And so you have the image that I've shown you before, this one with the final solution. And then these parameters of the new source are also written in a text file. This means that you can use it in other steps of another workflow, for example. And you also have figures showing the new synthetics, the old synthetics and the data. And in this folder, new scene, you will see the new synthetic seismograms in SAC format in a way that you can, for example, look at them, so what is the new solution and whatever you need. So just to tell you that when you will receive the credentials to log in into the Jupyter Lab that I will send after the webinar, under this folder, there are examples tutorial. You'll find the tutorial for the MT3D test case, the one that I showed you, and also the data folder with these template input files. And so you can test, you can copy this folder and also the tutorial in the home of the Jupyter Lab by just clicking on the file, right-clicking and say copy, and then you go in the home and copy, I already did it, the tutorial and the data folder, and you can execute it and look at the results and test the platform. Thank you very much.